All right. Hello, everyone. I'll go ahead and turn on my camera as well um, so that you can see me. My name is Casey Denham. I am an aerospace engineer at NASA Langley Research Center, which is located in Hampton, Virginia. But I'm here to talk to you today about engineering design at NASA. I do want to say out front, and I'll probably repeat this a few times throughout the presentation. Um, these are kind of my own thoughts and opinions. They definitely do not necessarily reflect the opinion of NASA as a whole or the US government. So there are, some of my own thoughts in here, but just want to make that clear before we get started. So a little bit about myself. So I'm originally from a very small town in Western North Carolina. Um, But I attended MIT for my bachelor's degree in aerospace engineering and then went on to Virginia Tech for my master's and Ph.D. in aerospace engineering. But I've actually started interning at NASA just 2 days after I graduated high school. So it's kind of a whirlwind weekend. I graduated on a Friday night, and then by Saturday morning, we had the car loaded up and we're driving across the state to go to the coast of Virginia. So I had five total summer internships through NASA's OSTEM internship program, and I'll talk about that at the end of the presentation as well. But then I was able to join the Pathways internship program while I was a graduate student back in 2018. So the Pathways program is more of a co-op style internship where you rotate between school and work. So it's a really great opportunity, and in most cases, it does result in a full-time job after you graduate. So that's what happened in my case. Once I defended my PhD in 2022, I was able to convert into a full-time employee, and I've been working at NASA ever since. I've really gone the entire stage from being a high school student obsessed with NASA, which hopefully many of you are, all the way to being an intern and now being a full-time employee. And my email's at the top, and Mahi has that as well. If you ever want to reach out to me and have any questions, feel free. I love talking to students. I always put a quick blurb about NASA when I do these outreach presentations because I think a lot of people don't realize all of the many different things that NASA does. So NASA is the National Aeronautics and Space Administration. It is a government agency that was founded in 1958 to further research into aeronautics and space. So I work on the aeronautics side of the house. I work on aircraft, not space. A lot of people are really surprised by that. But NASA was actually founded out of the NACA, the National Advisory Committee for Aeronautics, which was created in 1917 here at NASA Langley. And so NASA really has its roots in aeronautics, and the space stuff kind of came later after Sputnik. So one of the big things that a lot of people tend to misunderstand about NASA is we're not a commercial company. We are a part of the US government, so we're not here to make money. We're really here to do research and to further all of humanity. So a lot of times people will say, oh, why don't you do this? Why don't you do that? Because that's not what we're trying to do. We're really focused on the research and the achievements with that. And like I mentioned, it's not just about space. We have a large focus on airplanes, earth science, climate science, and many, many other types of research. I do always like to show this picture of different NASA locations. A lot of people, when they think of NASA, they only think of Houston for Johnson Space Center, or think of Florida with Kennedy Space Center. But we really have a lot of NASA centers scattered throughout the country. California, Texas, Florida, Mississippi, Alabama, Virginia, of course. So there's a lot of NASA facilities, and also each state actually has a state space grant, which is NASA's partner in that state. So NASA is really in every state, even if we don't have a physical facility in that state. And of course, I'm here at Langley Research Center on the coast of Virginia. So that's where I'm at. I also include this as well It's just kind of a word cloud I created with some of the different things that go on at NASA. Again, it's not just about space. It's not just about rockets. We have robotics, composite materials, human resources, communications, outreach. One of the things that I always tell students, and honestly, even adults that I talk to, is almost anything you're interested in, we have a job doing that at NASA. Um, a story I love to tell is that when I was an intern, I actually had a few friends who were interns. That same time, at the same summer, one was an art student, and her summer internship was painting murals around Center. So we have artists that work at NASA. Another student was a film student. NASA Langley and a couple of other centers actually have film studios, and we produce educational videos. We produce interviews of our engineers and our employees. We have a radio show. We have a podcast. NASA TV. So we have all of these different things. So I know you're all in FIRST Robotics now and like that aspect of engineering. But even if that's not what you want to do for a career, or even if you have friends who are not necessarily engineers or math focused, we have a job for you at NASA. All right, so moving on to the big topic of our conversation. What is engineering design? Since you guys are all high schoolers, I figured I would use one of your favorite tools, so ChatGPT. So I just asked this morning, asked ChatGPT, what is engineering design? So I'm just going to read the top bullet. Engineering design is a structured, iterative process used by engineers to create solutions to technical problems or develop new products, systems, or structures. And then, of course, it gave me a little bit more detail. So including a couple of different stages, so problem definition, research and analysis, conceptualization, detailed design, prototyping, testing and evaluation, implementation, and then feedback and iteration. So that's kind of what ChatGPT has put out. And then I also grabbed this little rainbow graphic from another website that kind of shows how it's a little bit more of a cyclical approach, not just a strictly numerical based approach where you do step 1 and then step 2 and then step 3 and now we're on to step 4. We do have that cycle. So you're going to end up repeating things. And so, I'm sure this is something that you all have experienced with through FIRST Robotics and probably in your science classes as well. I'm sure you've all learned about the scientific process and things like that, which is very similar to the engineering design process. And you can see there's some differences, but they're largely the same. And this is engineering design. It is. But design isn't always linear or even cyclical. So I think one of the things, and why I included this graphic on the right here, is especially when you're young and learning this process, it is helpful to think of engineering design as a process. We need to do this, and then we'll do this. Oh, and then now it's time to prototype. And maybe there is some iteration back in there, and you do a cycle, and you make some changes, and you need to prototype again. But in the real world, it isn't always that way. Yes, there are going to be cycles. Yes, there are going to be things that go in order, but sometimes it's going to be a little bit more like the maze on the side. And there are going to be multiple directions that you end up going at once. And sometimes you have to combine things back together. Maybe you have to jump further back in the cycle. Maybe there are new factors coming in late in the game and all sorts of things like that. So I think it's important as you're going through your design season this year, your competition season, don't get too focused on doing things in order, doing things in a process. Do what needs to be done. Another thing, going off of those two graphics, those two answers about what is engineering design, some of the things that were not mentioned in there, that really are some of the most important parts of engineering design, and I'll talk about these later today. They don't involve engineering at all. And I think that's something that, especially since you guys are in high school and you're still learning about this process, if you can really latch on to some of these larger concepts that are not just engineering focused as early as possible, it's definitely really going to benefit you both in college, but then in your careers for the rest of your life. So documentation, and I have a short example about this later on, but a lot of people, certainly me when I was in high school, have the mindset, oh, I like engineering, I like math, I don't like English, I don't like writing. But an engineer's job is documentation. You need to document what you've done and why you have done it. And that involves writing. And a lot of times, you also have to be able to share your work. So it's not even that, your teammates or future team members on your team and, future years have to be able to understand what you did. Sometimes you're going to present your work, whether that's to judges at the competition or whether that's to college interviewers, or whether that's, in my case, presenting it at conferences and showing off my work. That's all a part of documentation. And I know it's not fun. I know it's not necessarily enjoyable for a lot of people. But if you work on including that documentation as you're going through the design process and really make it part of the design process, it can, save you from a lot of problems. You don't end up trying the same thing twice, but it also makes your life easier once you have finished. Cost. Cost is another big one, right? You can have, the world's best rocket or the world's best aircraft, but it might cost you more money than you have. So there's a little bit of a trade-off there. And the same goes with time. Time is often included as a cost in a lot of our analysis. So it's not just about how much money you have, but about how much time you have. And that's really kind of independent of whatever you're trying to design from the engineering side. And the final thing is safety. And we'll talk about this a little bit more. You'll notice that neither of those definitions that we stated above really touched on safety, and really spoke about how you need to be designing things in a safe way and creating things that are safe. And that's something that's very important at NASA, and I think should be important really to everyone. So I'm going to give this first example, kind of a typical design process at NASA with one of my favorite examples at the moment, which is NASA's X-59 Quest. So Quest is one of our current X-planes, but it is a quiet supersonic aircraft. So it's trying to fly faster than the speed of sound. And currently supersonic flight over land is banned because it makes a loud sonic boom. If you've ever been to an air show, sometimes they'll do sonic boom demonstrations, but otherwise think about an explosion or a firework, that loud boom. So it's very disruptive to people, to animals. If it's close enough to houses, it can rattle houses, break windows, set off car alarms. So that's something that's just not acceptable. So we don't have supersonic flight over land. But X-59 is going to get that loud boom down to a thump. And I love it. So that's kind of the technical part of that. But you can see over on the right, there's actually 3 steps to the Quest mission. And so we're doing all of this aircraft development to get a quiet supersonic aircraft, which hasn't existed before. So that is its own engineering design cycle on its own. Then we have the second phase where we're looking at the acoustics of it. Did we actually get it as quiet as we thought? What does the sound profile look like? How annoying is that sound profile? How does it spread? All of that. And then the third part a sport that I'm really excited about, and that is community testing. So starting in about 2026, NASA is going to be flying this aircraft all over the country, all over different communities, so that many people can hear what this sonic thump sounds like. And they can decide, is this something that we would be okay with, flying over our house? Or is that something that um, is still not okay. But I'm so excited about that. I really um, hope that my city is one of the cities that's chosen to be one of the test cities. Um, I don't think they've made final selections yet, but I'm really excited to get to hear this sonic thump. So on the next slide, real quick, I'm going to share a video. Um, I'm a bit of a nerd. Hopefully you can hear the volume. But here's a quick video about X-59.
Supersonic air travel. One of those is reducing the disruptive sound to people on the ground caused by supersonic flight. NASA's Quest mission is the culmination of decades of research and is centered around a new aircraft called the X-59. NASA has contracted with Lockheed Martin Skunk Works to build a new full-scale X-plane to help solve one of the most persistent challenges, the sonic boom. Since 1973, the FAA has banned commercial transportation from flying at supersonic speeds. The ban was in response to the thunderous sound of a sonic boom, caused by shock waves created when an object travels through the air faster than the speed of sound. The Quest mission has two goals. First, design and build a unique shape that will reduce the loudness of a sonic boom reaching the ground to that of the sound of a closing car door. And second, once built and tested, fly over a number of U.S. communities to gather data on human responses to the sound generated during supersonic flight to find out if the noise is acceptable to the public. Then, hand over the data from communities to federal and international regulators to help establish a noise standard for overland supersonic flight. Researchers understand that there is still a need for the development of full-scale piloted X-planes to help close gaps in our understanding of aeronautic principles. The team will soon kick off a series of X-59 flight tests that could assist in opening new markets for faster air travel over land.
Sorry, it's not letting me get off that slide. Just a second. All right. So, sorry, I just love that video. I love the X-59. And so this is a chart that I pulled from a publicly released presentation talking about this X-59. I'm not even going to call it the entire design process because, there's not just one design process that goes into building an airplane or that goes into a project of this magnitude. There are many. This is really just the design process of the outside of the X-59. We have design processes that have worked on the engine, that have worked on the control systems, that have worked on, the pilot, everything that goes in, what the pilot needs, what he sees, how he interacts with the controls, all of that. But you can see here, I really like this graphic again because it's not kind of a strict linear progression. I actually really like how there's this kind of big right turn there, right? And you can see just before it, there were two options that they had to make a decision between. And I think that's a great example, again, of how the engineering design process works in practice. Sometimes you end up with multiple things and you have to down select. and sometimes you're going backwards. You know, there weren't any loops in this, but this was, again, only one component of it. And you can really see how much the design shifted from their original design, which is honestly a little short and stocky, all the way to the current X-59 design down here, which, you know, has this very long nose, as well as this, you know, very elevated T-tail at the top. So I just love showing how long or how much things have changed and how this process works. I know it's a little bit hard to see, so you can't really see on the dates, but, you know, down here at the top, you know, we're talking 2010 or even early 2000s for these designs. And then here we're talking, you know, 2014, 2015. And then, you know, this aircraft, as we saw in the video, it's just now being built. They actually just had an engine fire test for it a few weeks ago, and it's going to have its first flight in early 2025. So it takes a very long time when you have these very drawn out engineering processes. And I know that's not the case necessarily for your team for FIRST Robotics. You know, you have a very tight deadline, but you still can have, you know, this concept refinement, and getting the different ideas in there so that things are going to change over your season. You're going to change how you do your design. You'll probably learn things when you start building and have to go back and change them again. Second example that I'm going to talk about today, and I have the movie clip here because I have to include it, Apollo 13. So Apollo 13 is what a lot of people call a successful failure. So for people who aren't familiar with Apollo 13, for Apollo 13, shortly after takeoff, there was an explosion that damaged the fuel tank, and part of the command module, the capsule part for the astronauts, on their way to the moon. You know, this is only 2 missions after Apollo 11. So Apollo 11 happened, Apollo 12 happened, and then this is only the, you know, second one after that. And the astronauts were stuck in space for 3 days, with limited electricity, limited air, limited water, limited supplies, and they ended up living in actually the lunar lander, for those 3 days because of the damage to the command module and the energy requirements that the command module had. So they didn't make it to the moon. They quite literally failed at their mission to go to the moon and walk on the moon. But it was successful. No astronauts died. They were returned home safely. And that's, you know, one of the key things that NASA and everyone should care about is mission safety. And, you know, it really took a feat of engineering and of design, both by the astronauts who were in the spacecraft, but also by all of the crew on the ground to get them to return safely. So I'm just going to play a few minutes of this clip. It's pretty iconic from Apollo 13. If you haven't seen it, highly encouraged. It is a dramatization, but they, you know, talked with a lot of NASA employees, and, you know, they've read all of the reports. So it's a pretty good movie if you haven't seen it. Of course.
Coffee, please. Coming right up.
And it's an unskippable ad too. Sorry, everyone.
this is Houston. Say again, please. Houston, we have a problem.
So you get that iconic Houston, we have a problem. But good engineering and good engineering design really saved the day. So the first part, documentation, I mentioned it earlier, but documentation is, so important. And this is a great example why. So the crew on the spacecraft and the crew on the ground were working from the exact same documentation. They had the same instructions, the same procedures. They were working from the same set of knowledge. Imagine how different it would be if the people on the ground, only gave the astronauts a summary and they only had, limited instructions and they didn't have all of the full instructions. So having that documentation is very important. Prototyping. So one of the issues that they faced, during this 3-day journey was air filtration. Like I mentioned, they had to move to the lunar module from the command module, but there weren't as many air filters for the lunar module as there were for the command module, and the excess filters for the command module wouldn't fit in the lunar module. But crews on the ground worked to devise and test a solution using the same materials that the astronauts had, and they were able to build and prototype a design and test that it worked. And then they radioed the instructions up to the astronauts. So they really had to do that prototyping stage very quickly, but they still were able to do that prototyping stage of how do we build something, and what does it need to look like. And again, that iterative approach that is so important, that cyclical nature of engineering design. Again, when it was time to repower the command module, which includes the capsule, for them to return home, there was limited energy. These systems had been turned off for multiple days. Things were freezing over because it's very cold in space, and they weren't running heaters because of the high electrical demand. They couldn't power everything on. They had to figure out what the essential systems were, what order to turn them on, and how essential some of them were. And that was something that they had to repeatedly test. And there's actually a good scene in the movie that shows Ken Mattingly, who was supposed to be one of the Apollo 13 astronauts, but unfortunately was exposed to measles and couldn't go. But he ended up being very valuable because he was able to test things. As someone who had trained, with the crew, they did many tests until they were able to figure out what was needed. And then a unified goal and objective. I think this is something that, again, doesn't strictly fall under that engineering part of engineering design. But when you have a group, an organization, a team that is completely unified and has, a singular goal and objective, everyone's on the same page, everyone's working towards the same goal, that's when really great things can happen. And that's when, everyone's working towards the same thing. It's a lot more likely that it's going to get done. So that's where you end up with one of the big quotes from Apollo 13 and from NASA, is that failure is not an option. And just that idea that some things are not acceptable. And for NASA, for Apollo 13, that's the loss of the astronauts. So everyone worked together on this singular goal. And I know we're talking about FIRST Robotics. It's not quite going to be the same. If your robot design for this year doesn't quite work, no one hopefully is going to die, but having still that unified goal as a team to have the best robot as you can, I think is really important and really, helped in this situation. So these are kind of two examples of times when NASA has done engineering design really well. But I also wanted to give you an idea of what happens when it doesn't. So the Challenger disaster. In January 1986, the Challenger space shuttle suffered an explosion about a minute after launch, 73 seconds. And it destroyed, obviously, the Challenger space shuttle, and it killed all 7 astronauts that were on board. This is one of the single greatest loss of life that NASA has had. We had the Apollo 1 fire, we had the Challenger disaster, then we also had the Columbia disaster as well. And the Challenger disaster, as well as Columbia, really illustrated where failures in the engineering process, the design process, how we were operating led to that loss of life. And so this is a picture from the Challenger launch from that day before the explosion. This is a few seconds after launch, but a minute or so from this picture, we lost that shuttle and we lost those astronauts. So what happened? So there's a lot of ways you can break down what happened. The first is, what's the physics? What physically happened? What caused this? So there was a rubber O-ring around a seal, and it failed due to low temperatures, and it allowed hot exhaust from the nozzle joint to escape, and that was able to ignite the fuel tank. You can see here, this is an actual graphic from the incident report, and you can see here, out of all of this joints, it's 2 joints, and we have 2 tiny little black dots here. This is obviously part of a circular structure, so that's why they make an O-ring. But we're talking these 2 tiny parts, and this failure of a single one of those was what caused the shuttle to explode. So that's the physics side of it, but that really isn't the entire story. So what were the decisions behind what led to the Challenger disaster? So by 1986, when this occurred, this joint, the O-ring seal, it was already well documented that it had suffered damage in previous flights. You can actually see on the image, there are 2 O-rings. The reason there's 2 is because they had noticed damage, and they're like, we'll throw a second one on there. 2 can't fail, right? 2 is twice as good as 1. The O-rings had not been tested in cold weather. They're made of rubber. Rubber is brittle in cold weather. They hadn't been tested in cold weather. They were designed for high temperatures because they're next to this exhaust. But what happens if you take something that's very cold and then put it in something very, very hot? It's going to get damaged. And there was testing about what temperatures the O-rings could work at. They hadn't been tested this cold. There was a gap in the data. It was below what was the established temperature range for these O-rings. And people did speak up. People brought these issues up, right? Hey, we've noticed this damage. We don't think this joint is good. We think there's a risk here. Hey, it's really cold today. This is below what is acceptable for the O-rings. But they weren't listened to, right? That was not a part of the process. We talk about the engineering design process up at the top. That implementation is still part of the engineering design process. These were people who had worked on these parts and came in later, and they spoke up, but their concerns were ignored. The focus was on launching the shuttle, keeping a high tempo of operations, and really pushing forward. And so people were ignored, and 7 astronauts lost their lives, and we lost a space shuttle. So safety is everyone's responsibility. There were many, many, many points in time where the decision to launch at that temperature with the O-ring, with that seal, was made. So a single person at a single point in time speaking out and actually being listened to could have prevented that tragedy. And so I mentioned, along with the Columbia incident in the early 2000s, the Rogers Commission report for the Columbia accident, and then the Challenger incident report, the Rogers Commission report, and then the report about the Columbia accident really illustrated flaws in how NASA was operating at that time. Because although we had all of these design processes, we did not have those stop gaps in place for any person to be able to stand up and be listened to and say, I don't think this is safe. I don't think we should do this. And so we had not just one, not just Challenger, but we had Columbia as well. We had these preventable accidents that were, completely preventable from an engineering side, but they are also preventable from a safety and a personal side. And so I know this is a really serious example, but, today you're working on small robots and you're like, oh, people can't get hurt, blah, blah, blah. You can't see it on this video, but I have a pretty good scar on my hand. I was working on an engineering team project when I was in undergrad. We were playing with RC aircraft propellers. We are making, helium blimps. So we're talking like 4 or 5 inch propellers, tiny propellers. And, we're plugging them in, testing them that they worked. Wasn't paying attention and got my hand cut open by a propeller. So no matter how small what you're working on is, how silly it sounds, we were making helium blimps with trash bags, the potential for injury is there. And even though right now you're working on smaller robots, in the future, you might be working on an aircraft or a spacecraft that can endanger someone's life. And so that's why NASA really has a strong safety culture now. I encourage you guys to look through the reports from the Challenger disaster and from the Columbia disaster, as well as NASA's safety culture handbook, to really see how you need to integrate safety into the engineering design process. It's not something that you can separate out. It needs to be involved at every step of the way. All right, so I'm going to jump through some of the material at the end, but we will get these slides sent out to you so you can have them. So completely shifting gears, something more exciting. What can you do to be involved with NASA? So the biggest thing is OSTEM internships. This was the internship program that I participated in, right after high school and then all through undergrad. So these are single semester, single session internships. We have them fall, spring, and summer. Generally, these are going to be full-time and on-site, but there are some part-time and remote opportunities available. You just have to search for these. You can choose to apply to the same project again and again, or you can apply to different centers, different projects. It's a really great opportunity, but what I love about this program is it's available to high schoolers. So you only have to be 16 years of old, enrolled in school full-time with a 3.0 GPA, and be a U.S. citizen. So those of you who are juniors and seniors, this is something that is available to you. And we do have opportunities open for summer 2025. That application period closes towards the end of February, so you still have 2.5 months to apply. For high schoolers, you want to search for opportunities that are available for 11 or 12, and you can enter that into the search bar. If you're a current senior and you'll be graduating in the spring, you can also look for opportunities that are available for college freshmen. So there are literally hundreds of opportunities out there. I was technically a high school intern myself, but if you're interested in going into engineering, take a look at our internship program. Like I said at the top of the presentation, we don't just do rockets, we don't just do airplanes. Pretty much whatever you're interested in, we do have internship opportunities and later on job opportunities for you. There are also a lot of NASA competitions that you can get involved with. There's the Student Launch Initiative, which is something that you can start as a club at your high school. So it's a competitive rocket launch competition, and that has different divisions for middle school, high school, and college teams. And you're also grouped out in terms of experience. So if you're a first-time team, you're not going to be competing against a team that's been competing for many years. There's different levels there. A couple of different other competitions and opportunities, NASA Mines and Lunabotics, that kind of take you again through the engineering design process and get you more experience with that, as well as getting to work on things relevant to NASA and contribute to help NASA's goals. Just a final closing marks, as we're talking about engineering in general, I really can encourage you to get hands-on experience as early and as often as possible. FIRST Robotics is a great organization, and I'm so glad that all of you are participating in it. But I encourage you to not stop there. There are a lot of other opportunities that you can take advantage of. Model rockets, RC airplanes, other clubs and activities where you actually get to get your hands on things, learn how things work, learn how things break and how things get fixed. But it's so important, even when you go on to college. If you really are interested in going into aerospace and maybe one day working at NASA, I encourage you to join the American Institute of Aeronautics and Astronautics, the AIAA. So this is the professional organization for aerospace, and it includes scholarship and competition opportunities. It is free for high school students, but you have to be a member to get scholarships. So they have a couple of $10,000 scholarships that they award annually. It also opens you up to a lot of mentoring and professional development opportunities, even while you're in high school. And finally, don't be afraid to try, fail, and try again. That's another thing that I think isn't often included in the engineering design process. There's a lot of failure. There's a lot of trying things that don't work out. But it's, part of the process. And eventually you come out on the other side and have something that's even better because of previous iteration failed. I know we're a little late on time, but I'm happy to answer any questions that you have.
Yeah, so if you guys want, you can just kind of unmute, or you can also put it in the chat. That's also perfectly fine.
Do you have to be a U.S. citizen to intern or work at NASA? So for internships, yes, you have to be a U.S. citizen. And to work at NASA as a civil servant, as a federal employee, you do have to be a U.S. citizen. However, NASA has a lot of contractor employees that are employed by other companies, but they work side by side with federal employees, with civil servants. And a lot of those companies are able to hire non-US citizens. So actually one of my coworkers that's in my group that works side by side with us every day, he's not a US citizen. My boss was not a US citizen. He started as a contractor at NASA, and once he got his citizenship, he goes hired as a civil servant. So there, are some requirements, but there are some ways around it to work with other companies, but still work alongside us. Next question, how can quiet supersonic flight be possible? I know, right? But essentially it's all to do with the shape of the aircraft and the shape of the shock waves. So, and I am not a supersonics person. I work on urban air mobility aircraft. I work on regional air mobility aircraft. I don't work on supersonics, but the supersonic boom is caused by air compression, and specifically it's air compression kind of falling in on itself, and that's why it makes that sonic boom triangle shape. So what X-59 and all of our quiet supersonic work at NASA has been focused on is not letting that boom collapse on itself and not letting it form those triangle shock waves, but in kind turning it into what's actually known as a bow shock. So it is a curved shock wave, and that's a lot quieter. And because the compressions don't pile up on each other, it's not as strong, and it is quieter as well. So it still has a sonic boom if you go by like the physics definition, but it's a weaker shock wave. It's a weaker boom. And it's quiet enough that, NASA engineers think that it will be acceptable for humans to fly overhead. Another question, how many OSTEM internships can you apply for per year? There's no limit. As many as you want to. There used to be a limit a few years ago, and that has been taken away. So the OSTEM internship process, you upload your profile, and then for each opportunity, you just write, I think it's like 200 characters, a short paragraph about why you're interested in, that specific position. So once you have your transcript up there, once you have all of your skills and your resume loaded into your profile, it might take you 20, 30 minutes to apply to a position. So you could apply to 15, 20 positions over a weekend. And if you did that now, between now and February, you could apply to 100 or so positions. So there's really no limit on the number of positions you can apply to. I do encourage you, I know some students are like, oh, that's great, I'll just apply to all 500 positions. I don't recommend that as a mentor. Apply to the positions that you're interested in. I'm an aircraft person. I'm not going to apply to a position that's focused on space. I'm going to apply to what I'm interested in. If you're in high school, don't apply to positions that are only looking for graduate students, that are only looking for Ph.D. students. Apply to the positions you're interested in and are qualified for. Next question, what are the benefits of spending the time to document the iterations of the design? Wonderful, wonderful question. There are a lot of benefits, and a lot of times you don't necessarily see those benefits until something goes wrong. So I'll give an example from one of my student design projects. When I was in undergrad, I participated in Design Build Fly, which is an RC aircraft competition that's hosted by the AIAA. And so we'd go through many phases of prototypes and trying to test things. And eventually, we'd get something that worked. But then sometimes for whatever reason, later on in the semester, we'd have to change it. And because we didn't actually document what we had already tested, we had to sit there and go back and test again every single motor and propeller and electronic speed controller combination to find another one that worked. Um, Instead, if we had documented what we had tried before, we wouldn't have had to try those combinations again because we knew they didn't work. Another example is from my PhD dissertation. I was trying to do some fine tuning of an aircraft dynamics model that I was working with. So I was like, oh, we'll tweak this, and then I'll tweak that. Sometimes your code doesn't save. Sometimes your computer crashes. And if you don't have any metric of what you've tried before, sometimes that means you can't get back to that best result. Sometimes that means that you have to start all over. I know FIRST Robotics, you guys do a lot of coding, and you frequently will have a programming or coding team. Git, it's pretty useful. You can keep track of all of that. Git is one way of documentation. So, keep in mind what changes you made, what values you've tested, because it can save you a lot of heartache when something goes wrong and you either have to try and remember it or start all over. How do you approach collaboration during design? Yeah, so this is something that we deal with a lot at NASA, particularly within my work group. So my work group is focused on conceptual design of aircraft, and that's one of the reasons why I've shown the X-59, because it's something that a lot of my coworkers have had experience with. It takes a lot of different subgroups to work on an aircraft that complicated. You have people who are working on the outer mode line, the shape of the aircraft. You have people who are working on the propulsion, people who are working on the controls. You have all of these different groups who are experts in what they're doing, but they may not know that much about the other parts of the aircraft. So I think, it goes back to that common goal, that common objective that I mentioned with the Apollo 13 example. If everyone on the team is focused on kind of that one singular objective, right? Build a quiet supersonic aircraft, build the best robot for our team, then you can kind of shy away from things where it's like, oh, we have to do this because we're the propulsion team and we're the best team and we're better than all of the other teams. When it's true, that might be the best answer for propulsion, but that's not the best answer for the entire aircraft. So I think when you're working on collaboration on a team with a lot of different subgroups and a lot of different specialties, you have to have humility. You have to know where you're not the expert on something. And you also have to remember the common goal. And don't get caught up on, this is what's best for our team or for me personally, but you have to do what's best for the group overall.